Whew. So we will discuss probably not today. Today is the biggest day in the class, and especially in the lab. But by next week, please develop your opinion to make a practice democracy. If we present on Friday, it gives you less time to prepare. If you look at your schedule, because 1 hour could be insufficient. 19th of December is a little too close to Christmas. I will follow your decision. Just think. So what we have to do today is there are two parts of just in case if you like to see yourself. We need to complete a couple of academic sections, and it will be about half and half. First half about accomplishing research projects in general, and it is summarized in this little piece of paper. In the second half will be primarily for Stephen as a client. But for the rest of you, it will be just curiosity in case you practice more in PR. So for practical work, there are a couple of things to mention because I'm not declining my own words that project is possible to complete in 1 hour, but one needs to have a very clear plan. If there is no plan, it can be 100 hours. And there are similarities between individual projects, but they all are different. And they need to make a common what is common, especially if you're not doing chemical. If you're doing chemical reaction, it's very simple following the pattern. If you're doing something different, you need to define which parameters and what will be the responsive system to which parameter. Then there is an idea that we repeat again and again, but it is not literally required, but very comfortable to organize thoughts in research effort so that everything we do can be summarized in a single number as a function parameter. Then one summarize multidimensional thinking and research effort into like y as function of x curve and explain what it is. And this, for most of the projects, it will be a rate of reaction fitting into a range. Or I'll tell explicitly what are other parameters for other projects. And then for the second half of the meeting, which will be a continuous series of entertainment about physical chemistry, I will try my best to repeat the last lecture on harmonics. It is an exaggeration. It will be not literal, but there will be a lot of analogies. If we remember what was there, I don't remember it 100%, but very direction. But there can give a little agenda right now and then just find the good slides. When we were completing the section on oscillating oscillator, we decided to predict where the center of the oscillator will be. And for our practical tool, we did a Heisenberg equation of motion for creation and manipulation operators, which were rotating forward and backward. And then, by definition, we added them together and obtained a position information. Right? So two complex oscillatory functions by adding together with sine or cosine. Then you see that position oscillates and momentum oscillates, and in phase space they make a circle. There will be very much the same approach 2 nuclear magnetic resonance. There are no oscillators anymore, but there will be creation and conservation of the. There will be equation of motion for those. They will perform as a complex phase oscillation, positive and negative, and by adding them together, when we get either ascending, we get projections of magnetization. So that magnetization performs cyclic rotations. To some level of extent here, we got many ideas. I'll try to do some technical details. Okay. So if you're doing chemical reactions, it is fine, but some of the projects are not chemical reactions. Helium and steam. Special. And it's really good to identify a parameter and find an observable that depends on this parameter. The parameter is something that you can change continuously. For amelia, it could be angular momentum, how quick it rotates. For Steven, right now I'm telling something that will be not clear for the rest of the class, but I'm talking to the camera, hoping that Steven will watch. There is
I am watching.
Okay, good. You see this blue text. So in your code, in your project, there is an ensemble of many doublet spins with slightly different frequencies. And you can control energy offset between them, and you can overall width of this distribution of the disorder. So your parameter could be width of disordered distribution. And your observable could be the rate of reinduction decay, how quick the magnetization decays with time. Make sense?
Yes, I was planning on something similar to that, I believe.
Super. For John, it will be C1 and C2 coefficients by adding together two quantum states in this rotating wave packets in 2 dimensions. You will have 2 dimensions, two wave packets, one prevailing and another smaller or in equal measures. And for observable, it is very creative. I do not have clear vision, but we'll chat about it. Maybe hypothetically, one can set up an observable for total angular momentum. If it rotates one way, it will be positive, other way, it will be negative. If it is superposition, it will be negative. Okay, so it is general motif. Find how the observable depends on parameter. For typical chemical reaction, the parameter is momentum, which corresponds to temperature, and the observable is rate. Okay? So you have seen this slide, right? So I'm going to focus on 2 boxes, cyan and magenta, and they are printed in your printouts. So need to practice water. So most of us are computing the one-dimensional wave packet dynamics, and we can convert it into probability distribution, right? The probability distribution can be split on the left and right part, which is reacting to the product. Or for Morgan, who is not here, but maybe he is watching, it will be like probability in one parabola or another, one another one. So it's integrating probability distribution from beginning to the middle, and from the middle to the end. It will be like two curves, probability of reacting and product, like shown here, right? Which need to be normalized. And then here is a little bit non-trivial thing, an approximation that may or may not work, but is good to follow because with simplicity. For many chemical reactions, and you may know it better, there are zeros, first, second order reactions. And in this specific case, the change of concentration feeds into exponential form. Okay? If the change of concentration and this probability of reactant and product is equivalent in your chemical reaction orders, like concentration that you put in the square brackets. So if this concentration as function of time behaves in the exponential way, okay, then there is a very simple mathematical procedure that I'm skipping because of my laziness. I will verbalize, but no doubt that every one of us can do it. So if one has numerical data for all points of time and all points of the concentration of the probability of product, like here or there, one can numerically integrate left and right part. On the left part, it will be integral of the product concentration. On the right part, it will be integral of exponential. The integral of exponential will be exponential, but the factor, the rate, will come up. And one can solve for this rate, for the k. So it will be concentration of product at infinite time divided by integration of product as function of time minus product at infinite time. And it is either implemented in some versions of code or it is one line to practice. So as soon as you have this line, one can. So basically, it is what Excel does by fitting curve to exponential function, extracting the power of exponential. You are free to practice different curves and different protocols of fitting. I'm suggesting the simplest. Like the exponential is the simplest one is linear, next one is exponential. Good. Questions or objections? Okay. But let's scroll our mind backwards. This is only one trajectory. Okay? What you are changing momentum, which corresponds to temperature. And you are getting these curves again and again for different momentum. So for each momentum, you get different value of k. And this is the most time-consuming part of the project. So you are setting up different value of momentum, converting it just for the record, converting it to kinetic energy and to the temperature. Kinetic energy with Boston constant gives temperature. And then you record the yield and rate in the integral formula that was in the previous slide. So momentum versus rate, or energy versus rate. It's not here, but if one multiplies this by Boston constant, you get temperature. Temperature and rate, two coordinates. Make sense? As soon as you did the table, your project is basically done. The rest is straightforward, maybe 15 minutes more. So I invite you to watch on the magenta here. Just before our meeting, I looked into Wikipedia that he almost failed his doctoral thesis, but later got the prize for it. Which means if you do something really novel, it's often rejected by the community. So you are generating a set of data, values of temperature, which for Boltzmann constant times temperature is, which is kinetic energy, and rates of reaction. For consistency, I probably need to put the same symbol used. So in the simplest case, the table does is represented by 4 numbers: temperature, T prime, T over prime, rate, K, T prime, T over prime, right? And if we take logarithm of left and right part of the Arrhenius law, so here the logarithm of rate equals minus activation energy on the thermal flow, right? And one can plug in, one can solve this equation for activation energy. Okay. So it will be derivative of logarithm of rate over derivative of inverse time. Okay. And if you do not like derivatives, you just need 2 points. One point is time and rate, another point is time and rate. And on the, if you just solving for this equation, in the numerator it will be difference in logarithmic rates in one point and another one, and in the denominator will be difference of inverse temperatures. I'm not showing an illustrative figure, but if in other classes and in reading, probably Svante Arrhenius will not be offended if I draw on his face, because it is his theory. Because of nature of this equation, instead of dependence on temperature, it is very comfortable to put dependence as function of 1 over time. What it 1 over temperature. When I heard it from my instructor in my time, I was very angry. What's wrong with temperature? Why should we use 1 over temperature? It's a crazy parameter. But just for equations, for this type of equation, it is much more comfortable. And typically, the dependence, your points will look like curve going this way. And depending on this, it's not case, logarithmic case. And depending on the slope between logarithm of rate and inverse temperature, it will be different activation energy. I am speaking right now as a technician. And if I imagine myself on the other side, one can lose the goal of this narration. Why you need to spend your precious time on so many laborious steps? What is the benefit in that? If you extract or design a potential for your favorite reaction, you can immediately assess approximately the activation energy, which intuitively should be related to the height of the barrier. But your old baggage of quantum theory tells that wave packets sometimes can sneak into places where they are not expected to be. And there is a chance that wave packet will tunnel through the barrier. And it happens in the nature all the time. And it often happens that the activation energy assessed through this procedure will be noticeably smaller than the height of a barrier. And for many practical reactions, it is an important piece of information that cannot be analyzed without your knowledge in physical chemistry.
Is that what they call tunneling?
Yes. If you find that for your system tunneling is big, you report it. If you find it is not, you also report it and tell it. I have hypothesized, but prove it wrong. Yes?
I see the A in the first equation, but I didn't see that in the second
It
equation.
cancels.
Excuse me.
It cancels.
Oh.
If you process it, you can divide left and right by A, and when you take logarithm of RT prime over A, and here will be R K T double prime over A. Logarithm of fraction is subtraction of logarithms, right?
Yeah.
And it will be minus logarithm A minus logarithm A, and it cancels.
Is that a constant?
Yes. If you want to reproduce rate back out of these parameters, you need it. But if you just need to extract activation energy, it won't calculate. So here is nothing mandatory. It's just suggested way how the written reports may look. You do not need to have 7 figures. Do not be scared. It's just an option. But when you do something from previous years, there is a trend. From my own experience, first, when I need to do something, I'm afraid of extra. It's so many things, I better do nothing. And when you put your hands on, you're getting very easily the human nature excited and generate more data that is fitting into format. And then you more need how to shorten the data and how to simplify the representation. So if you can do like 1 or 2 figures instead of 7, great. I'm just suggesting template for the logic. Like schematic diagram of problem, potential. About eigenstates, I will tell about eigenstates at the very end of today's lab, if time will allow. It's a cool stuff, but it is technical. Examples of typical dynamics is when you, instead of movie, you show 3-dimensional code of this blue diagram. Calculation of product as function of time. It is basically the step from which one is extracting the rate. The rate as function of momentum, rate as function of temperature, and the data that later feed into the LNU score. Please give me a sign who never opened a single research paper. So you all are exposed to see how research paper looks like. So there is a typical way to reduce number of figures that keep the same number of information. Figures are combined in the panels. You call it, my paper has 1 figure, but it is lie. It's like 6 panels. Figure 1, A, B, C. Okay. Done with projects, and everyone except Steven can just relax. In years, I plan to redo this figure in typing and make it more visible, but we are browsing. Someone literally decided to relax. We are browsing in space of theories the different models, and there is another degree that we almost do not touch, but another degree is perturbation, external light, field, heat, and evolution shows the evacuation density of states later operator, and we went through free space, boxes, column, oscillator, rotator, and now we are going to spin. So this is the little dictionary that we covered during our last meeting. So spin, not for to speak in public, but it is like rotation of electron around itself clockwise and counterclockwise with a fixed rate. And there are two states, up and down, and there are weather operators that promote it from up and down. We can talk about it in the space of two states, which are represented by in this vector space of dimension 2, with two basis vectors. And then transitions from up and down can be set as 2x2 operators. And if one multiplies these two operators in different order, one is getting projectors. Projector not like a lamp with a mirror, but a projector in mathematical sense. By acting of this operator on a quantum state, one parses specific probability, probability between one and another state. If one adds together these two projectors, one would get the identity. If one subtracts them, one is getting the inversion of the rate. I plan to show it with equations and in details, but even with a little heads up. So expectation value of this operator will be probability that system is in state theta. Expectation value of this operator is probability that system is in state alpha. Adding together these two probabilities will be 1, identity. Subtracting them will be positive if it is in beta, negative in alpha, 0 if it is in superposition. This idea, especially 0 if it is in superposition up and down, is relevant for Steven and for John. Like if you will be trying to use observable as angular momentum, if it rotates one way to be positive, other way negative, if it is superposition, it will be 0. What is my goal if time allows? What do I want to show? Those who care. There is an important traditional language to describe spin, and it is based on this ladder operator technique. But their spin is connected to linearization. Linearization is a vector with 3 components. And here we do have 4 vectors. What is a connection between expectation values, operators, and projections of magnetization and projections of spin? The physical meaning of projections of spin are the same as 3 projections of angular momentum. Like, although electron can have only the globe, this pseudo globe, is allowed to rotate clockwise and counterclockwise, but the axis can be at any angle. Therefore, we can extract projections of these simple rotations in 3 directions. And one needs an algebraic way to connect matrices of operators to these three projections. So this is my little goal number one. Little goal number two is to show that no matter what you do, projections will rotate to extract law of motion for these projections. Because law of motion projections in spin are naturally connected to magnetization that is measured in the NMR and EPR experiment. And as I gave you a little heads up, it will be very similar to harmonic oscillator. So it's Bohr magnetron. So the goal is to arrive to this slide. The adding together expectation value of creation and annihilation operator for spin will give projection of spin and correspondingly of magnetization onto x-axis. Subtraction of the creation and annihilation operators of spin will give y projection of spin and y projection of magnetization. The subtraction of projectors to upper state and lower state, the inversion, will give the projection of spin on z direction. And projection of magnetization. So these three things give three components of a vector. Vector of spin or vector of magnetization, which will perform like a little arrow showing a point on the surface of a globe, depending on the external conditions like static and oscillating magnetic field. Magnetization will keep the length of this arrow, but will be oriented differently. And if you solve for this creation and annihilation operator, which is like simplest possible differential equation, one will get that x projection will be like cosine, y projection will be like sine, and the z projection will stay constant. So if one set up a vector that origins from the center of the globe and points on the surface, the spin projection and magnetization that observed in the will most typical motion will be traveling across the equatorial line. So what is the connection to real life? When, at which conditions does it happen? So an NMR experiment is spins are from nuclei, right? And there is a strong magnet that creates a constant magnetic field, and there is a lower intensity but not constant oscillating magnetic field in transversal direction. The constant magnetic field in z direction determines the pace of this rotation and energy offset of the lower and upper state. If I will decide to offer us Zeeman effect, it will be connected. If not, then we'll hear it in some other, but the energies of co-rotating and counter-rotating in magnetic field split. The stronger magnetic field, the bigger the split. The bigger the splitting, the quicker rotation. The transversal magnetic field is tuned to have the same frequency as frequency of this rotation and used to convert this vector from ground state to excited, from rotating one direction to another one. By duration of this irradiation with oscillating magnetic field, one can promote it completely or halfway. And these pulses, inducing pulses, are very short. So one creates this promotion and then switch transversal field off. And when this vector is let alone with only constant magnetic field in the z direction, it performs this equatorial motion. Okay. Often the sphere is called the Box sphere. The scientist who decided to represent magnetization spin in this if x projection is cosine, y projection is sine, and z is constant, it is exactly the equatorial motion. Okay, 10 minutes before that, if we start. So how does one get it? We do the same thing. We do Heisenberg equation of motion of the creation and annihilation operator with Hamilton. So we already know what is this creation and annihilation operator for spin, and we need a Hamiltonian. I believe we did it in the last 30 seconds of previous meeting, but I'm not sure if anything was left in our memories. So we do, and I completely imagine myself on the other side and understand that this density of information, nothing is possible to remember. It is more like a fairy tale to be repeated in some other courses and in a mosaic way to develop memories. So we do have projectors on the state alpha and state beta. And if you put energies of state alpha and state beta in front of these projections, then the summation of projectors will be a Hamiltonian. Good? Or like a noise? Yes, yes I can. Maybe, since I'm already presenting the main outcome, even if we delay a little, or even skip it. So, S plus S minus, it will be projection on B. S minus S plus will be projection out. If we add them together, energy of state B times beta beta plus energy of state alpha alpha, it will be Hamiltonian. So beta beta is 0, 0, 0, 1, alpha alpha is 1, 0, 0, 0. If we do this Hamiltonian, it will be E alpha E beta 0, 0. Hamiltonian is diagonal, right? And it is just Dirac form of expressing Hamiltonian. And this, if in the weather operators, it will be E beta S plus S minus plus E alpha S minus S. So by placing energies of states in front of projector operators, one is getting Hamiltonian. Now, in order to practice, how do you in order to practice Heisenberg equation of motion, for creation operator, we need to find commutator of this operator with Hamiltonian. If we plug it in and do this little operation, which little derivation is kept here. E beta S plus S minus S plus minus plus. So if we think about Hamiltonian as we defined on the previous slide, and we try to multiply it by S plus from left and right, and practice all rules that we learned. Then here it will be 4 terms, right? This one 2 terms, this one 2 terms, and it is multiplied. But if one carefully does it, the operators will cancel each other. We will get energy of state alpha S plus minus energy of state beta S plus. If you just carefully do this operator algebra, which means energy difference of the states times the creation of the operator. And if we believe this operator algebra, or if we spend another so many minutes to prove it, then equation of motion for the S plus operator will be derivative equal operator itself times difference of energy. Right? And you can solve it by dividing left and right on the S plus, and then on the left it will be only unknown, on the right it will be only time, and one is getting the solution of the creation of operator is equal to operator at the initial time times the phase accumulation in complex phase. We always can put angular brackets to highlight that we are looking at an expectation value rather than abstract. If we practice the same operation for annihilation operator, this green formula is for Morgan. I will cover it next time. So if we practice, here it is skipped operator algebra. It is not written, so I should just pronounce it. If you do practice this operator algebra for annihilation operator, the solution will be the same, but energy difference will be with sign minus, and it will accumulate phase in the opposite direction. A little comment that you may need in other courses, on the graduate courses if you go to graduate school, and a little bit in the CHEM2. What is similar and different for these pairs of creation and annihilation operators for harmonic oscillator and for spin? I completely understand your attention is already distracted by many things I'm presenting. But what I want to focus attention is here. No, there's a messy slide. Remember, when we were doing commutation of creation and the annihilation operators for oscillator, when we subtract them from each other, it was getting 1. You remember it. Here, in order to get 1, we need to add together products of creation and annihilation. Now, who cares, plus or minus? But in this case, so we need to look on this little line, S plus S minus plus S minus S plus gives identity operator. And here one needs to creation and annihilation subtracted to get an identity operator. So this is fundamental property of particles with spin 1 and spin 1/2. Because of their different commutation relations, they have different statistics. Bose statistics and Fermi statistics. Right now, I'm not proving, I'm just declaring. Due to this anti-commutation property for spin, for fermion, we have Pauli exclusion principle. So it is not possible to put 2 electrons into the same state. two electrons should always have different set of quantum numbers. And it is naturally connected to this property of quasar. If you have oscillations or another bosons like photons, we can create as many particles into the same quantum state. And in the CHEM2, there will be far-going consequences of these different statistics for bosons and fermions. So for an integration operator, it revolves in the opposite direction. And now if we add together S plus and S minus, we will get cosine if we get an overtime. And some of you have plans for the rest of the day. So sine and cosine. And if one practices subtraction of this thing and put Bryant cat for any true quantum state, like alpha and beta, C sub alpha, C sub beta, alpha and beta bra, C alpha star, C beta star. If one practices this for inversion operator, one will get constant. It will not change in time. So for X and Y projection, there is dynamics, and for X and Y there is dynamics, and for Z there is no dynamics. Therefore, it proves this nice stick man traveling along the paper. Enough. Next slide will be just yellow confirming that lecture is done. Thanks much for investing your time, and looking forward to see you on the evening lab session. Yes. Not watch. We need to set up an appointment. It's today's lab is the main meeting of the whole class. It's not replaceable by watching. 5 p.m. tomorrow.
Yeah.
Let's exchange emails for